What's up, guys? It's John. This is my fifth lab, and I chose to do it on collision. So, quick intro. What I did was I wanted to see if I could make a real life elastic collision between two pool balls. So I hit two pool balls together, and I videoed it and put it into Tracker, and then I pulled that data and put it into an Excel spreadsheet to find the velocity and position functions with respect to time, and then I put that velocity and position into the Python to find a computational model for it. And so I utilized the energy and conservation of momentum principles for this lab, and the goal was to determine if the computational model or if the real system exhibits a fully elastic collision. So the physics principles that I used was the change in kinetic energy is equal to 1/2 m delta v, and then also the conservation of linear momentum is that the sum of the initial momentums is equal to the sum of the um, final momentums, and that's if it's elastic. So if it's elastic, that should be true, and the kinetic energy should be zero. If it's inelastic, the change in kinetic energy should not be zero. So this is some information because I hit the cue ball into the strike ball. As you can see, the cue ball had an initial velocity, a pre-collision velocity of negative 1.615, and it had a post-collision velocity of 0. As you can see again, it goes and it hits the strike ball and it just stops. And the strike ball had a pre-collision velocity of 0 as it starts from rest, but a post-collision velocity of negative 1.688. And it's important to note that the two balls had different masses. So these just show the x position with respect to time for both of them, and the flat is just because the purple ball started at rest and the cue ball ended at rest. So these were my calculations. So a kinetic energy of the cue ball initial was equal to 0.226 as it had a velocity associated with it. And the kinetic energy of the strike ball, since it didn't have any velocity, was 0. So then the kinetic energy of the cue ball final, because it collided and stopped, it had a velocity of 0. And then the kinetic energy of the strike ball um, had a kinetic energy of 0.222 as well. So based on our momentum principle and our energy principle, um, these hold true, and we have delta Ke is equal to 0. Um, so this is my code. I added two balls, had the different masses of the balls, um, had the position, the initial conditions, and then my while loop to iterate through is just updating the cue ball position based on its velocity for up until the collision, and then after the collision, updating the position of the striped ball, the purple ball. So you can see in my computational model, I've got my cue ball. This is where it collided with the purple ball and then sent the purple ball flying and it stopped velocity from the origin. And then this is actually a combination of the two um, graphs of the different positions. So as soon as one position ended, the other started. So this is showing that because it's a totally linear line, um, it the collision didn't have any effect on the change in position. This is showing a difference in velocity, but that is accounted for in the momentum principle because um, the the while the strike ball had a higher velocity, while the strike ball had a higher velocity, the cue ball had a higher mass. So higher mass, smaller velocity, but lower mass, higher velocity evened out to satisfy our momentum principle. So was our energy principle satisfied? Yes, energy principle is satisfied, and it exhibited fully elastic collision as velocity came to 0 after the collision, and the strike ball gained all of the kinetic energy. And possibility of error was friction from the felt, energy being released as sound or heat from the contact, and then inaccuracy with the placement of the center of mass for tracker on both of them. the balls.